like to start by thanking the organizers for this amazing workshop. I think it's going to be very productive. And I'll start by talking about massive gravity. Usually when I talk about massive gravity, I spend quite a bit of time motivating modifications of gravity. But since we're in a conference on extended theories of gravity, I'll be a bit quicker this time. But let me just motivate it by different aspects. The first one is that there's little data we're going to need to modify gravity, at least in the UV. And what I'll take, the approach I will take here is more to understand whether it's possible to modify gravity in infrared, so at very long distances. And at the origin, these modifications of gravity arose from the observation of the late time acceleration of the universe and the cosmological constant problem. And since then, it has kind of taken a life of its own. And when modifying gravity, the first step is, well, constructing a theory of modified gravity which is consistent in the first place. And then the second stage will be finding some relevant, if you want to use it for cosmology, finding some relevant cosmologies. And I'll talk a little bit about that today. And then as a next step, we really will need to find some observational signatures for these theories to see whether they have anything to do with the real world. So the approach I will take is really to understand whether the late time acceleration of the universe and some naturalness problems, such as the cosmological constant problem, may be the first sign of the breakdown of the theory of GR on very large distance scales. And when we want to tackle the dark energy problem, we can take two different approaches. First one, we can just ignore the cosmological constant problem in the first place, just set by hand the vacuum energy of particle physics to 0. Maybe there's some hidden symmetry that we don't know of, which sets it to 0. And then find another way to source the acceleration of the universe. So that's the approach behind dark energy. And in dark energy, we can really think some additional components which was what we usually think of dark energy, like quintessence of these kind of models, which are really additional new degrees of freedom in the matter sector. Or we can think of modification of gravity, which will generate new degrees of freedom, but they are encoded inside the graviton itself. In both cases, the new degrees of freedom can lead to a late time acceleration of the universe just from the energy density present in these new degrees of freedom. So that's one approach, and that's where one reason modifying gravity can be relevant for dark energy. Another approach is to try to reconciliate the amount of vacuum energy we would expect from particle physics and the amount of acceleration we observe at late time. And of course, there's some naturalness issue there, but maybe if we change the natural scale, maybe the natural scale for vacuum energy is not the Planck scale, not the TV scale, but another scale. Or we could try to keep the scale of the vacuum energy and having set a large vacuum energy driving a very small acceleration of the universe. And in that case, modified gravity, and originally massive gravity, was thought to be our way to achieve that aspect. So modifying gravity could lead either to a way to reconcile the vacuum energy with the observed acceleration at late time, or lead to dark energy and explain the late time acceleration of the universe. So that was the starting point. But really, what I'll do today is try to present some theories of modified gravity and see how they can be relevant, if they can be relevant at all for cosmology. And I remain quite agnostic on which side of this graph we are. Now, as we know, GR is a very beautiful theory, and it's very unique in a lot of sense. And as soon as we try to modify gravity, specifically in the infrared, we are led to many instabilities, and specifically ghost-like instabilities. And one approach that has been quite successful in achieving consistent theories of modified gravity is to start with GR itself. Since it's so consistent, if we start with a five-dimensional theory of gravity, that has been actually quite successful in obtaining theories of modified gravity, where gravity behaves effectively as a massive graviton at large distances. And that's the approach I will do. And there are two different kinds of approaches, starting from 10D gravity, which we can take to have a theory of 4D massive gravity, either the DGP one or the hard mass gravity. And each one of them is related to Galileans in some specific limit. That's why I'll talk a little bit about Galileans. So if we start with 5-dimensional gravity, in order to recover 4-dimensional gravity at small distances in the UV, one way to do that is to confine gravity on a brane, and that's the idea behind valid Gavazzi-Porati model, where we have an infinite extra dimension, or a very large extra dimension, but our world is sitting on a four-dimensional brane where gravity is also induced there. And effectively, from a four-dimensional point of view, we have a graviton which has a mass which depends on the momentum, so that's a soft mass, and the mass scale that enters there is the ratio of the five-dimensional to the four-dimensional mass scale. If we look at the spectral representation, it looks like effectively we have something peaked around zero mass and then a distribution. So it really corresponds to a resonance of soft modes rather than discrete massive mode from a four-dimensional point of view. And in some limit, the five-dimensional effectively scalar degree of freedom, or the brane bending mode in this setup, looks like a Galilean. It has interactions of this kind of nature in addition to its normal kinetic term. And these interactions are, of course, very important to explain the Einstein mechanism and to recover four-dimensional gravity near very dense regions of space-time. In this case, where we just have one infinite extra dimension, the spectral representation is peaked around zero, so even though it corresponds to a theomassive gravity, really it's dominated by zero mass in the spectral representation. But if we go to higher dimension, the spectral representation is peaked around a finite mass, and so that starts looking a little bit more like a theory of hard mass gravity, but it's still a soft spectral representation in the sense that there's a resonance, there's no discrete mass in that case. So if you go to higher and higher dimension, it will start looking more and more like a pure theory of massive gravity. So that's the idea behind theories starting from five dimension where you have an infinite extra dimension. But as an alternative to inducing gravity on a brane, what we can think of, and what is probably more natural originally, is to start with a finite size extra dimension. And that's quite natural because if we start with a finite size extra dimension, we would expect to have a zero mode, where we have no dependence along the extra dimension, and that zero mode will be massless from a four-dimensional point of view. That will correspond to the zero mode here in the spectral representation. And then on top of that, we have a series of Kaluza-Klein mode, which corresponds to a series of massive mode of the zero mode. And so this is just this tower of mode in the spectral representation. And so this really corresponds to a Kaluza-Klein decomposition. Actually, what I'll represent, it's a little bit easier to do, is not a discretization in Fourier space, but a discretization in real space. And so I will really discretize directly the extra dimension rather than doing it in momentum space. And we will have something which looks also like that, and is actually equivalent to a Kaluza-Klein decomposition after a nonlinear field definition. That's the idea behind deconstruction. And the idea behind deconstruction was shown to work very well at the beginning of, well, 15 years ago for gauge theories, but it was thought not to work as well because of strong coupling issues in the case of gravity. And actually we can see that it does the job in the case of gravity as well, if we know how to do it. And the idea is to start with a finite size extra dimension, and we will be working the field-bound formalism. There's different reasons for that, but the main motivation is really is because it works if you do it in the field-bound language. But more physically, fundamentally, all the fields matter field will eventually couple to the field-bound language rather than the metric directly. And so it's more natural to discretize in the field-bound language rather than directly in the metric language. And discretizing in one or the other language actually doesn't give rise to the same result. So if we start with five-dimensional gravity, and I split this five-dimensional gravity, the Einstein-Hilbert term, into a four-dimensional one, and then some extrinsic curvature, which corresponds to the derivative along the extra dimension. And now what we do is simply replace this continuous extra dimension by a finite number of sites. This is a discretization in real space, and at any site we have a metric which depends, which has a field line localized at that site. And so if we discretize with n different sites, we'll have n different types of field line. And so we expect to have a theory with n interacting gravitons, and that's indeed what we have. So the four-dimensional curvature term leads to something which looks like a four-dimensional curvature term after discretization as well. But the derivative along the extra dimension is what actually will link different field bands with one another. And that will give us some interactions with the different metrics from a four-dimensional point of view. And they lead to a four-dimensional potential interactions between these four-dimensional field bands of metric, And that's what leads really to a theory of multigravity. And here I've just written a U potential, but it's important that it has the precise form given by the 5-dimensional extrinsic curvature term. You can have a little bit of freedom into how you discretize, how you treat the field by doing this discretization, but when you do so, you only have a finite, actually a two-family parameter of a possible potential term from a 4-dimensional point of view, which is inherited from this precise structure from 5 dimension.
But then the distance between these sides is very large because n is very small, right?
The capital N?
M.
Yeah, M is going to be very small eventually. Yeah.
Yeah, but then you replace derivative by a finite difference.
That's right. That's right.
And
yeah.
since the coefficient m is something like delta x in
that's right.
the
That's right.
denominator.
The distance.
Yeah. The distance is very large between the sides.
Yeah.
But then you cannot use this formula.
Well, it's a motivation really.
It's a motivation.
Yeah. But if you discretize, it's only if you think there is something in between that this discretization will be wrong. Yeah.
But is there a reason why you stop at
The reason why I start with what?
So you write the potential as a function of the metric in one side and the metric in the next side. But you could also take the higher order interactions with the next side.
That's right. Okay. Yeah. So if you have some free, this is the basic notion of the derivative. You can extend this notion of derivative as well, and I will, out of this specific structure, it will give you a little bit more freedom. But ultimately, what's important is that you have this structure of k minus k squared there, which will dictate the way the interactions go. So in this very specific way to do it, you only have, in multigravity, you only have interaction with nearby neighbors. When you have a whole theory of multigravity, it doesn't need to be the case. You can have interactions with any other graviton that you like. I will focus eventually on bigravity and then massive gravity, so this distinction is irrelevant. But in principle, out of that, by extending this notion of derivative, you can have more complicated potential. Yeah. But the key thing is more coming from that rather than anything else. Yeah. So you obtain from a 4-dimensional point of view a theory of multigravity, which is, so it's true that in this case, it's a specific case of the theory of multigravity proposed by Kurt and Rachel a few years ago. And then this theory actually goes free, and it's one of the examples, well, it's not one example, but it's a special case of these standard theories of multigravity which are shown to be goes free, also in the field of language. Now, I will focus for the rest of this talk in 2 sides. So that's more of a motivation. And in these 2 sides, it's true that this distinction of how exactly you take this discretization is irrelevant. And so if you do the discretization in 2 sides, and this is just a motivation, we're not thinking that this is the real world, that we're living in an extra dimension, which is discretized. It's really more of a motivation into starting with a 5-dimensional structure of gravity, which we know has no ghost, and then try to use that to get a 4-dimensional structure for 4-dimensional modified gravity, which is also goes free. And it seems that starting with 5D gravity ensures us that from a 4-dimensional point of view we have no ghost. This is not quite true actually. It's really because we knew the result beforehand that we can use this as a motivation. If you try to do this discretization directly in the metric language, you obtain a theory of 4-dimensional gravity and multigravity which will have ghosts. But we'll do it the way I presented before, and so if you do the discretization with 2 sides, what you have is a theory of bigravity, where you have 2 different interacting metric, and their interactions is dictated by what was the extrinsic curvature from a 5-dimensional point of view. And in that case, you have, when you do the spectral representation, Laplace space, we end up with one massless spin-to field, one massive spin-to field, leading to 2 degrees of freedom in the massless spin-to field, 5 degrees of freedom in the massive spin-to field corresponding to 7 degrees of freedom. And this bigravity theory is a special case of the general. Bigravity theory is proposed by Rachel also a few years ago. Another way to do the counting here, and I'll go back to that later on, is to think of having 2 different metrics, independent metric, one in the G, one in the F, and then some interactions there. If you didn't have the interactions, then you have 2 copies of diff invariance, one for the G metric, one for the F metric, and so you have 2 degrees of freedom in the F metric, 2 degrees of freedom in the G metric. And then this interaction breaks one copy of diff invariance, which can be restored by introducing 4 Stucker-Bell fields, this phi, in 4 dimensions there's 4 Stucker-Bell fields, and one can show that out of these 4 Stucker-Bell fields, only 3 of them are independent. So that leads to 2 degrees of freedom in G, if you want, 2 degrees of freedom in F, and 3 degrees of freedom in the Stucker-Bell fields corresponding to 7 degrees of freedom. That's a back of the envelope way to count it. Of course, the degrees of freedom are hidden in everyone, so it depends on how you want to do the counting. Now, out of this theory by gravity, we can take the limit where we send the Planck scale of one of the metrics to infinity, and that has for effect to freeze this metric, to decouple one of the metric, leading to a theory of massive gravity on a fixed reference metric. And a fixed reference metric doesn't need to be a background, doesn't need to solve some background equation in motion, it can be any reference metric one wants. So we can split, for instance, the F metric into a reference metric like this, a fixed reference metric like that, and then the fluctuations on top of that, which are canonically normalized with the proper Planck scale. And sending the Planck scale to infinity leads for this mode to something which is just a linearized massless spin-2 field. And then we have for the other sector a theory of massive gravity, so the G metric with the interactions of a mass term leading to this reference metric. And in that case, we have 5 degrees of freedom in the theory of massive gravity plus 2 degrees of freedom in the decoupled massless spin-2 sector. So that leads to 5 degrees of freedom plus 2. The number of degrees of freedom is the same eventually, but now we can just take this theory of massive gravity and live by itself. Yeah?
So why do you say the F metric did not satisfy the equation of motion?
Here I haven't assumed that it solves anything.
It has to, I mean, if you get it as a limit of biometrically, it has to solve some equation, doesn't it?
I mean, everybody has it. You have some G equation and you have some F equations, but I mean, this is, you can take that theory and you can take the F split like that and take the limit when F goes to infinity.
Yeah, then you will have linear terms also in perturbations. Yeah. F has to solve it. F bar has to solve the equation of motion.
Yeah, the F bar to satisfy G mu is 0 or G.
Yeah, but you can put any matter. You can do whatever you want. You can. I mean, you can. If you want to read it on shell, but with any type of matter that you want. I can think of that as something which is off-shell without precising what the matter sector is for that measure.
Then you have also matter sector for the second mate.
That's right, but it decouples as well.
That's right.
So
That's right.
Takes care of
That's right.
itself.
Yeah. But in that limit, the matter sector won't couple to this thing. You can make it so that they're independent. So you can do the counting with that as well. But for anything I want, I can think of adding a matter sector. For the F metric.
Yeah, but if the F metric is not a solution, then the perturbations will couple linearly to the background of G.
No, but it is a solution with some
It
matter.
has to be a solution, yes.
Yeah.
Solution with some
Add some matter such that it's a solution. So whatever G mu nu, the Einstein tensor you want it to be for this F metric, add some matter sector T mu nu which satisfy the correct equation with the interaction with the other metric.
Sorry, but why is this matter sector not suppressed in the limit MF goes to infinity?
You do the same thing. So you have in this matter sector, you have some part of it which will couple to the matter, to this metric, and will source whatever reference metric you want it to be. And then you can have fluctuations on top of that, which will decouple. It's your choice to decide how you want the matter sector to behave in the
So you're
limit when
scaling the
MF.
matter sector as well?
You have a matter sector as well, yeah.
No, but you're scaling it as well. Because
You scale that as well, yeah.
Yeah,
okay.
You take a decoupling limit on the matter as well, so that it all makes sense.
Yeah, but it's all your choice. You can go through all of that. But the bottom line is that whatever you want this F metric to be, and it doesn't need to solve the vacuum equation of motion for the F metric. So you can do whatever you want to do. Up to, I mean, at this level, I'm not even imposing any specific conditions on the matter sector for this F metric.
I mean, if I would have started with mass gravity without taking the limit, there will, as well, I mean, I see immediately that F bar doesn't need to be the same back on it, you will expand it. So it can
Oh
be
yeah, yeah.
arbitrary.
Oh yeah, definitely F bar is something, in this area F bar is completely independent to whatever happens here. Yeah. So F bar is completely independent to the vacuum solution for the geometric, definitely. Yeah. Okay, so out of that you get a theory of massive parity. And then the key thing again is that the specific structure of the interactions here, which I haven't written explicitly because it's a bit complicated, but you can see it there, is inherited from the in that case, from the 5-dimensional way the extrinsic curvature arises. And so you can see a little bit that the extrinsic curvature from a 5-dimensional point of view will lead in the most natural case to this something that looks a little bit like an extrinsic curvature. Now these are purely 4-dimensional quantities which relate the one metric with the other metric. Here I've taken the eta mu metric, so it's the case where this F bar is just eta. That's one specific case, but you don't need to do that necessarily. And then depending on how you do the discretization, you can have all the parameters coming in. You can have all the type of potential entering, but it's really just a 2-parameter family of possible potentials that would lead to a ghost-free theory of massive gravity. And there's nothing else in 4 dimensions that it could have written down. Here that takes a very specific structure, which leads to no ghost. Of course, when you write this out of this K mu, K mu, which is inherited from the 5-dimensional one, you don't need to put this delta if you don't want to. You can put a 2 here, or you can put a 26 there if you want to. These are just field definition, which will lead to slightly rewriting of this potential. The reason why I like writing it like that is because if you're working on perturbation around flat spacetime for this metric, then this term here really corresponds to the mass term, to the field volume mass term about Minkowski. But if you don't care about that, then you can really make a theory definition of these things. It doesn't lead to anything, to any different theory at all. And this theory has been shown. It's not enough, of course, to say that we started with a ghost-free theory from a 5-dimensional point of view to say that it is ghost-free from a 4-dimensional point of view. Something could have gone wrong, and in many cases in the past things went wrong when doing that. Fortunately, in that case, it's been shown that this theory is fully absent of ghost, fully non-perturbatively, and that has been shown now in many different languages by many people, including especially Forward, present here, and Rachel, and then many other different languages in the literature. So I'm not going to go through the proof of the absence of ghost. Ask people in the audience if you want them, if you have any questions about it. Okay, so to go a little bit to the counting of degrees of freedom again, and to see the similarity between massive gravity and biogravity, that's more or less what I said before, again, where we can think of, in a theory of massive gravity, it's a theory of a massive spin to field. And a massive spin to field, and this fluctuation of flat space-time, should have 5 degrees of freedom, which are hidden 2 into the helicity 2 mode, 2 into the helicity 1 mode, and 1 into the helicity 0 mode. The helicity 1 mode, effectively, at least from cosmological purposes, they behave as vector field, and they're more or less irrelevant for many of the cosmological discussions I will be talking about. So long as they are stable, but they don't really lead to additional energy density leading to any source for the daytime acceleration of the universe or anything like that. However, the helicity 0 mode couples directly to matter, and so a lot of the phenomenology of this theory of massive gravity is really coming from the existence of a new effective scalar degree of freedom, rather than just the modification of the helicity 2 mode with a mass. So that corresponds to 5 degrees of freedom, and once again we can think of that counting slightly differently, of having 2 degrees of freedom in the metric if we fix the gauge, and then 5 degrees of freedom in the Stukabel fields. So this term that enters in the mass term, that breaks explicitly diff invariance because of the eta mu doesn't transform as a tensor and the field coordinate transformation. But we can promote this quantity into something which will behave as a tensor by introducing 4 Stukabel fields. And once we introduce the 4 Stukabel fields, then we have diff invariance. Then we can fix any gauge we want. For instance, we can fix unitary gauge where the Stukabel fields are just XA, and that's one specific gauge. But we can use these Stukabel fields to set any gauge we want. And so we can think of that as 2 degrees of freedom in metric, and only three of these Stukabel fields are independent. So 3 degrees of freedom in the strip of fields. And in massive gravity, the counting is exactly the same. The only difference is that we have an additional massless spin-2 field, so that is to 2 additional helicity 2 modes, and we can do the counting into the helicity language, or the counting into the degrees of freedom in the metric, plus the 3 additional Stuckelberg fields also present in here. To restore the second copy of diffie-invariance, that should really be present in gravity. So it's very similar in both cases.
Hey, Claudia?
Yeah.
I'm sorry. We have had a discussion before. Are you sure that Stuckelberg fields really encode the helicity 0 and helicity 1 into the freedom of the massive mode? You don't.
If you fix a gauge?
No, I mean, if you compute the gauge invariant TT correlation function, the correlation function for the massive gravitational sandwich between 2 stress energy tensors that are conserved, you see that the Stuckelberg field completely drop out.
But it depends on your gauge.
No, I mean,
choose
you
a
don't
gauge where they're not there.
No, don't just completely gauge invariant. The Stuckelberg fields are gauge mode. They do not couple to conserve energy momentum tensors.
Yeah, but
I mean, what you
we're saying the
see?
same thing. I mean,
What you-
of course
No,
the TT
so-
amplitude
So
gives
yes,
you the physical answer.
but your massive graviton always carries 5 modes,
Yes,
irrespective of what gauge you choose.
yes,
So if you couple massive graviton to conserve the energy momentum tensor,
that's
the
right.
massive graviton does carry, the interactions are carried by 5 modes, even though Stuckelberg fields do not couple.
No.
Yeah, it's quite easy.
It
to
depends
see.
on your gauge. If you bring
No,
in,
this is
if
gauge
you work in
invariant.
unitary gauge, the 5 modes are in the metric.
No.
If you come out of unitary gauge, then 3 of them are in
The
the
5
Well,
modes
so-
of the
so
matrix are contained in the gauge invariant part of it.
Yeah,
It's the
exactly.
TT part of
What
the
you're
gauge.
computing is gauge invariant, right?
Yeah, but the
TT
TT
amplitude
part is
is.
gauge, so the TT part of the matrix is gauge invariant.
That's right. That's right. So
Exactly.
you can't say what the degrees of freedom are.
No, so the Stuckelberg fields are gauge modes.
Yeah,
They do
but
not
what
enter
you're
them.
saying is trivial. That's the essence of the Stuckelberg trick. That's always true.
No, but that's the statement that the 3 helicities are contained in the Stuckelberg field is not true.
No, but that's a statement about if you work in a given gauge, you can
No, in
move the
any
degrees
gauge.
of freedom.
In any gauge, that statement is not true.
No,
in any
come on,
gauge.
come on. That's,
Social gauge invariant variables is also like not a unique choice. So
No,
every gauge invariant choice basically corresponds to some gauge.
Look. Okay, I can show you. Just write the propagator for the massive graviton sandwich between 2 stress energy tensors.
Yes. So this is gauge invariant.
Exactly.
That's right. So then you don't.
So
when you
now-
compute this gauge invariant quantity, then you can't say, oh, but the degrees of freedom are
Yeah.
into
So
the
if-
Stuckelbergs or the other
Exactly.
things.
So Stuckelberg fields,
So they are hidden into the whole.
no, they are not there.
but that's the
No,
essence
no,
of the
no,
Stuckelberg
So they
trick.
cannot carry helicity 0 and helicity 1 because helicity 0 and helicity 1
No,
are
come on,
physically
that's-
present.
Of course, in a gauge invariant thing, they don't contribute because they're gauge modes. But the essence of the Stuckelberg trick is that it's convenient for certain purposes to, in a given gauge where you put the degree of freedom in the Stuckelberg field. Of course, you can also set it to 0. You don't need it.
Yeah, but helicity 0 and helicity 1 modes of the spin-2 field are there, isn't it?
Yes,
Maybe
they're always
that's-
there.
Degrees of
They're always
freedom
there.
never change.
They're always there.
Yeah.
In
I mean, this is
Overrun's
just-
gauge, they would,
Sorry?
in Overrun's gauge, they would be there. The spin 0 would contribute, like what
That's
she's
right.
calling the scalar, it would contribute
That's right.
to this amplitude.
In unitary
No,
gauge, they're not there because
you can compute the gauge. You can look at this gauge invariant quantity and you see that the Stuckelberg fields do not contribute there.
In Overrun's gauge, they would.
Yeah.
So let me work in unitary gauge.
Sorry,
Let me work
let's
in
continue,
unitary
let's
gauge.
continue.
Then I fix unitary gauge.
Yeah.
Then of course the degrees of freedom are not in the Stuckelberg fields because
So
I fixed
in
the
the
gauge for
TT
them, and they are in the H.
In the TT
But I can work in
correlator,
another-
Stuckelberg field completely drop out. Sorry,
No, that
I just wanted to make a
Kurt
comment.
says
sorry.
that in Rhams gauge they contribute because there's a mixing between the scalar part and the H, and you have to diagonalize that, and so you do get a
No,
coupling between the
when you
Stuckelberg
compute the
fields and
TT
macro.
correlator, that is completely gauge invariant.
That's gauge
It
invariant.
does not depend on what you
Yes.
But where the different parts come from doesn't.
I'm not sure you can even compute the, I mean,
You can.
You
the
can.
propagator doesn't exist in the gauge environment.
No, in a,
No, you can compute it, and the
massive spin-2,
the
there's no
Stuckelberg
gauge
field
invariance.
couples to matter after diagonalization.
I mean, not putting the environment.
Sorry, no. It was just a comment.
It's good because I thought I was repeating myself. It's good to have the same statement a few times. Okay, so I think we all agree that there's 5 degrees of freedom in massive gravity and 7 degrees of freedom in bi-gravity. Exactly how we want to interpret these degrees of freedom is I'll leave it to your discretion. But now that we have a theory of massive gravity, and I'll focus on that side, I'll talk a little bit about bigravity in a bit, but when we focus on massive gravity, and most of these statements are actually valid for bigravity as well. But we can ask the question of how unique that was, because we start with a theory of massive gravity, gravity in 3D as an inspiration to get a theory of 4D massive gravity, and that's actually after the fact. But we can ask whether there isn't anything more general than the theory that we wrote down. Specifically, that we started by introducing a mass term for the graviton that breaks, before introducing the Stucker fields, that breaks diff invariance. And if you break diff invariance, you may wonder how unique the kinetic term is. The kinetic term of GR is the unique kinetic term you can write down for a massless spin 2 field, but if the spin 2 field is massive, maybe there's something more generic you can write down for the kinetic term. And actually it's been shown by Kurt and by other people that at the linear level, if you just want to think of a theory of a massive spin 2 field without interacting to matter sector, the kinetic term, the Einstein-Hilbert term that you usually write down, which this is the Discretization operator that you usually write down, is not a unique one. You can also introduce a new interaction, which is a cubic interaction, which has a very similar structure than the standard kinetic term, which is cubic in the field perturbation, and this is about flat spacetime. And this theory goes free by itself. Now, if you want this sector to have, if you want this theory to have anything to do with gravity, you want this H mu to couple to matter. And once you couple to matter, you're going to need to promote linear diff to nonlinear diff to coordinate transformation invariance. And when doing so, you need to promote these interactions to their nonlinear completion. And the nonlinear completion for this term is the one on Einstein-Hilbert term, nonlinear, the square minus GR. And this one potentially could have a ghost-free nonlinear completion, but actually you can see, at least in a metric language, that this term has no nonlinear completion without leading to a ghost at the same scale at which this interaction enters. So in this sense, this interaction, the standard kinetic term for gravity, is also the unique kinetic term for a theory of massive gravity, at least in a metric language, because any other term will lead to a ghost at the very same scale at which it enters. So there's no regime where we could have this term being interesting without also leading to a ghost at the same scale. So the kinetic term itself is unique. Now we can ask the question about the coupling to matter. And I haven't mentioned that so far, but in all of these cases so far, we're thinking of the coupling to matter motivated by what it is in GR. And so we would have, for instance, a matter sector which couples to the metric G in a massive gravity, just in the same way as you would have in GR. And so if the mass term wasn't there, this would completely preserve diff invariance. It's just a covariant way to couple to matter. But what I can do, once again, we're not limited to that case anymore because we've broken one copy of diff invariance, even though we can restore it. And for instance, we could think of a sector which couples not to the dynamical metric G, but rather couples directly to the reference metric F. And that type of coupling is also ghost-free. In a theory about bigravity, that would correspond to having a sector of matter coupling to one metric and another independent sector of matter coupling to the other metric in the bigravity case. In principle, one can think of something even more general, that any other case where you have both metric entering here will lead to a ghost at the same scale. Apart from one very specific combination where we could have coupling to matter to yet an independent sector of matter, which couples to an effective composite metric, GF, which in the field-bound language corresponds to linear superposition of the field-line of the dynamical metric and the field-line of the reference metric.
Alpha and beta are constants or functions.
Alpha and beta, they're just constant, yeah. Actually, yeah, that's a good question. Yeah, I don't think you, I have to think on the spot here. It's possible that one might be able to promote these parameters to functions of the Stucker fields. Yeah, I think that's true. Yeah, like I would. That's a good point actually. Yeah, that could potentially be
Well, functions are another matter, like another scale. Probably would work.
No, but if that other scalar has its kinetic term, which couples to this metric, that won't work necessarily. Because then its kinetic term will have a kinetic term coming from that and a kinetic term coming from this, and this coupling will lead to a ghost. Yeah. So it's true. Maybe there's something a little bit more general than that if you want to. I think of the Stukable fields, this can be functional. So this is a new type of coupling, which is ghost-free for a new independent matter sector, which is ghost-free in a specific decoupling limit. And in general, at least in the metric language, it will carry a ghost in the full theory. But there is a regime where we can consider this matter coupling by itself without a ghost limit, and specifically working with decoupling limit. And that can have some interesting consequences for cosmology. The last thing we can ask to generalize is the mass term. And this mass term inherited from the 5-dimensional setup, these two parameter family of mass terms, is actually the unique set of terms or combinations which leads to no ghost in the decoupling limit and in the full theory. But while one can do something slightly more general along the lines of what Misha is mentioning, is to promote the parameters which are present in these combinations to themselves functions of the Stukable fields. And this will lead to no ghost. This is a generalized theory of massive gravity. A generalized theory of massive gravity where, so this UN are the combination of the K terms that I wrote before. There's a quadratic, a cubic, a quartic, this can be linear as well. And so you can promote this two-parameter family to a 2 or 3 even function family of the Stukable fields. And by the very way the Stukable fields enter here, we see that this combination is Lorentz invariant. So this is a Lorentz invariant theory of massive gravity. And we can do the constraint analysis, so we can do the counting of degrees of freedom in the same way as we did before. This doesn't introduce any kinetic term for the Stukable fields, because it's just functions of themselves, not of their derivatives. So the counting of the degrees of freedom is exactly the same as before. And so that leads to 5 degrees of freedom. It doesn't have any ghost issue, and you hold as a ghost in that case. However, this is not a promotion, a generalization. This is not directly a nonlinear extension of the Fields-Pauli theorem of massive gravity, because it actually breaks translation invariance. And the easiest way to see that is to work in unitary gauge, where the Stukable fields unitary gauge is just is XA. That's what I mean by a unitary gauge. And so F mu, which is eta AB mu phi B. In unitary gauge, that becomes eta mu. But in that gauge, in unitary gauge, this function of the Stukable fields just becomes x squared, and so that breaks translation invariance. So this is a theory which breaks Poincaré invariance, even though it doesn't break Lorentz invariance. And
so the function of this alpha, that can be anything. Is there any constant in that, or it can be any kind of?
This alpha here?
Yeah.
In order not to have any ghost, there's no constraint. In order for this theory to have anything to do with the real world, you want to have constraint. Phenomenologically, you have strong constraint. And then if you want, so I'll go through that, but if you want some theory to do cosmology with that, which is stable, and which maybe leads to self-acceleration or something like that, then we'll have strong constraints. Yeah. Specifically on themselves and on their derivatives. Yeah, so if this function is just a constant, we will cover the same thing as usual. Yeah. Okay, so in the last, not in the last 3 minutes that I have, I'll start talking about the main point of this part. The relevance for cosmology. So let me start with the bad news, which is something we knew from the kind of the beginning, but we still can do something with this type of theories. If you start with a theory of massive gravity, with a flat reference metric with a flat Minkowski reference metric, then this flat reference metric has fundamentally a different topology than the zeta, which is kind of the topology we would like to have FRW solutions. So in a theory of massive gravity with a flat Minkowski reference metric, and by flat I mean for the spatial curvature, there cannot be any homogeneous FRW solutions. So that seems like a bad news, but actually it might be quite natural. And one way to see that is that the very constraint in massive gravity that removes the ball weight as a ghost is also what prevents the theory from having this type of FRW solutions. Let me just go quickly into how you can think of that more intuitively, at least for me more intuitively, is that if you have a theory of massive gravity and you put the Stucke fields in, then the only place where the Stucke fields enter is into the promotion of this eta into a full tensor. And so when you derive the Stucke equation of motion, you obtain a constraint which is a derivative of the potential, which ends up becoming a time derivative of a function of the scale factor A, which has to be equal to 0. Because the Stucke fields definitely don't enter in the kinetic term, and if the Stucke fields don't enter in the coupling to matter, if you preserve the standard matter coupling to matter, you just left with this constraint, which tells you that really you don't have any FRW solutions. So that's the end of the story in this case.
But you can have a solution which admit nevertheless the translation of Killing vectors, three translations. You take de Sitter, rewrite it in fast slicing, and of course de Sitter admits translations. But if you write it in fast slicing, it will be inhomogeneous.
Right, exactly. So that's a very, when you do that, you make a very strong assumption on the Stucke fields themselves already. This statement is also assuming something on the Stucke fields which you would think of them more as standard degrees of freedom and decide that they only depend on time, and that's a consequence of that. But of course, we cannot be observing something which is just FRW and having some inabilities instead in the Stucke fields. Yeah, absolutely. And this is something I put in here, and it's true that so weighs out against this absence of FRW solutions in massive gravity with flat reference metric is to have some inhomogeneities into the Stucke fields. It doesn't mean that what you observe is inhomogeneous, but there's some inhomogeneities present there. So I think I'll just go through this graph these different options very quickly, and I'll conclude here, and then I'm happy to answer any other questions. But there's been a lot of different alternatives. People have been trying to find some FRW solutions, or to find something which looks like FRW within our observable universe, so as to be able to do cosmology with that. So one possibility, which is still very open, is to break Poincare invariance, just like I'm sure we can break translation invariance. We could break Lorentz invariance, and when we do so, we have much more freedom, which allows actually to have exact FRW solutions. There has been some work in the literature which is now, I think, not working so well. One possibility is to, instead of working with flat...
Claudia,
yeah?
with much more freedom, sometimes can be fixed. There are some residual symmetries that also can be due to be minimal, let's say, not that you completely open.
Oh no, yeah. No, that's not what happened. Yeah. It was meant in a good sense. Actually, yeah. Yeah. No, of course, yeah. I mean, you have constraint on what you can have here as well. Yeah. You can promote the reference metric to. Sorry, I was here. You can instead of working with a flat Minkowski, especially flat, you can have an open solutions, and having especially open FRW solution allow you to have the open Minkowski metric then start having the same topology as the de Sitter one, which is what allows you to have exact FRW solutions. Unfortunately, this has been shown to suffer from strong coupling and unstable solutions. The same thing happens if you try to promote the reference metric to another reference metric, for instance, the Sitter of FRW. That not the same thing happens, but you have problems with Igor Ghost and Matteo, who is here, and Andrew and other people have been working in this direction and show that this actually seems to be more or less a dead end. Another alternative is to include new degrees of freedom. These new degrees of freedom can be in a scalar sector. For instance, if you have FFR, massive gravity, really you have a new degree of freedom you have a new scalar degree of freedom. You can think of mass varying massive gravity, quasi-dilaton, and this type of theories, which all allow for exact FRW solutions. I think the extended quasi-dilaton, and so in some cases the quasi-dilaton itself, allow for stable self-accelerating solutions. And a direction that many people here have been working, so I think we'll hear about that, is to really work in bigravity. And I'm not sure so much work has been done for multi-gravity to get FRW solutions, but for bigravity. And in this perspective, that corresponds to adding new degrees of freedom, in this case, it's a tensor mode. Now it seems that this direction leads to a special case where you can have an exact FRW solutions which is compatible with observations and free to any type of pathologies and instabilities, but I think most of them have gradient instabilities, right? So maybe you'll hear more about that in the rest of this conference. And two directions I've been working on is the one in generalized massive gravity, where you break translation invariance, then the promotion of the parameters to function of the Stuckable fields allow more freedom to really give exact FRW solutions, which can be self-accelerating and can be stable with no ghost, no tachyon in any of the degrees of freedom. And you can also think of the new couplings to matter. So if you allow for Stuckable fields to enter in here, that modifies the constraint there in such a way that exact FRW solution can be present in the theory. So I don't have time to go through these two different cases in detail, but I'm happy to talk more during the break or anything. But I have to say, I think the most natural solution to this observation is the fact that inhomogeneities can be carried by the Stuckable field, and the universe itself, we don't expect it to be homogeneous on arbitrarily large distance scales. So it's quite natural that at a very large distance scale, the universe itself will be inhomogeneous, and we should really start looking at this type of solutions. Then, on shorter distance scales, the Rham mechanism will be active into hiding these homogeneities and having something which is as close as we want to FRW cosmology. So let me stop here. Another direction I haven't mentioned, which I should have, is the introduction, the working with non-local massive gravity, which also allows for exact FRW solutions. Okay, so let me stop here.